Today, I invite you to explore the remarkable life and enduring contributions of one of the most influential scientists in history, Max Planck. Known as the father of quantum theory, Planck transformed our understanding of the physical world and laid the foundation for many of the technological advancements we enjoy today. His work marked the beginning of a scientific revolution that changed physics forever and opened new pathways for exploring the mysteries of nature. The birth of a scientific visionary to understand the extraordinary legacy of Max Planck. It is important to begin with the story of his early life and the environment that shaped his character. Great scientific achievements rarely emerge in isolation. Behind every groundbreaking discovery lies a journey of learning, curiosity, perseverance, and personal growth. The foundations of Planck's revolutionary contributions to physics were established long before he introduced the concept of quantum theory. They were rooted in his childhood, education, family influences, and his unwavering commitment to intellectual excellence. Max Carl Ernst Ludwig Planck was born on April 23, 1858, in the city of Kiel, located in what was then the Duchy of Holstein. He entered a world that was rapidly changing. The 19th century was a period of scientific advancement, industrial growth, and intellectual exploration across Europe. New discoveries were transforming society, and universities were becoming centers of innovation and research. Although no one could have predicted it at the time, the young boy born in Kiel would one day become one of the most influential scientists in history. Planck came from a highly educated and respected family. His father, Johann Julius Wilhelm Planck, was a distinguished professor of law. Several generations of the family had been involved in academic and professional careers. This intellectual atmosphere played an important role in shaping Max's outlook on life. Education was highly valued in the Planck household, and scholarly pursuits were encouraged. Rather than growing up surrounded by wealth or luxury, Max grew up in an environment where knowledge, discipline, and achievement were considered the highest goals. The influence of his family extended beyond academics. His parents instilled in him strong moral values, a sense of responsibility, and respect for hard work. These qualities would remain with him throughout his life. Even after becoming one of the most famous physicists in the world, Planck was known for his humility, integrity, and dedication to truth. These characteristics were developed during his formative years and became central elements of his personality. When Max was still a child, his family moved to Munich, one of Germany's leading cultural and educational centers. This relocation proved significant because it provided him with access to excellent schools and intellectual opportunities. In Munich, he attended the renowned Maximilian Gymnasium, where he received a rigorous education in mathematics, science, literature, languages, and philosophy. At school, Planck quickly demonstrated exceptional abilities. He was not necessarily viewed as a child prodigy in the dramatic sense often associated with famous scientists. Instead, his strengths lay in his consistency, concentration, and determination. Teachers recognized his remarkable analytical skills and his ability to understand complex ideas. He showed a particular interest in mathematics and physics, subjects that allowed him to explore the logical structure underlying natural phenomena. Interestingly, Planck was also deeply interested in music. He possessed considerable musical talent and became an accomplished pianist. He could play several instruments and had a strong appreciation for classical compositions. Throughout his life, music remained one of his greatest passions. He often remarked that science and music shared important similarities. Both required creativity, discipline, and an appreciation for harmony and structure. This connection between science and music reveals an important aspect of Planck's personality. He was not simply a mathematician focused on equations. He possessed a broader intellectual curiosity and an appreciation for beauty in many forms. This combination of analytical precision and artistic sensitivity contributed to his unique approach to scientific inquiry. As Planck approached adulthood, he faced an important decision regarding his future career. Although he excelled in multiple subjects, he felt particularly drawn to physics. At the time, however, physics was not considered an especially promising field. Many scientists believed that most fundamental questions had already been answered. The major laws governing mechanics, electricity, magnetism, and thermodynamics appeared well established. One of Planck's professors reportedly advised him against pursuing physics, suggesting that there was little left to discover. According to this view, future scientists would merely refine existing knowledge rather than uncover entirely new principles. For many students, such advice might have been discouraging, yet Planck responded in a way that revealed his character and intellectual independence. He explained that he did not seek to discover new things merely for fame or recognition. Instead, he wanted to understand the fundamental laws of nature as deeply as possible. This response demonstrated a profound commitment to knowledge itself. He was motivated not by ambition, but by curiosity and a genuine desire to comprehend the universe. In 1874, Planck enrolled at the University of Munich to study physics. There he began receiving formal training from some of Germany's leading scientists. University life exposed him to advanced theories and experimental methods. He immersed himself in subjects such as mechanics, thermodynamics, and mathematical physics. Among the topics that fascinated him most was thermodynamics, the study of heat and energy. During the 19th century, thermodynamics had emerged as one of the most important branches of physics. Scientists were seeking to understand how energy moved through physical systems and how natural processes obeyed universal laws. Planck became particularly interested in the concept known as the second law of thermodynamics. This principle describes the tendency of natural systems toward increasing disorder, often referred to as entropy. Many scientists viewed the law as one of the most fundamental truths in nature. Planck was captivated by its elegance and universality. His fascination with thermodynamics reflected his broader scientific philosophy. He believed that nature operated according to objective laws that could be discovered through careful reasoning and observation. Rather than focusing solely on practical applications, he sought deeper theoretical understanding. This emphasis on fundamental principles would later guide his revolutionary work on quantum theory. After completing his studies in Munich, Planck continued his education at the University of Berlin. Berlin was one of Europe's foremost centers of scientific research, attracting brilliant scholars from across the continent. There, Planck had the opportunity to learn from renowned physicists such as Hermann von Helmholtz and Gustav Kirchhoff. Although he admired these scientists greatly, Planck often found their lectures less inspiring than he had expected. Instead of relying entirely on classroom instruction, he developed the habit of independent study. He carefully examined scientific papers, analyzed complex theories, and pursued his own intellectual questions. This self-directed approach strengthened his ability to think critically and solve problems independently. Independent thinking became one of Planck's greatest strengths. Throughout his career, he demonstrated a willingness to question assumptions and explore ideas that others overlooked. His success was not based solely on intelligence, but also on persistence and intellectual courage. In 1879, at just 21 years of age, Planck earned his doctoral degree. His dissertation focused on thermodynamics, reflecting the subject that had captured his imagination during his university years. Completing a doctorate at such a young age was a remarkable achievement and signaled the beginning of a promising academic career. However, the path ahead was far from easy. Academic positions were highly competitive, and young scientists often faced years of uncertainty before obtaining stable employment. Planck encountered many challenges as he worked to establish himself within the scientific community. Despite these difficulties, he remained committed to his research and continued exploring fundamental questions about energy and physical laws. One of the defining characteristics of Planck's early career was patience. Unlike some scientists who achieve rapid recognition through spectacular discoveries, Planck spent many years building expertise and refining his understanding. He approached scientific problems methodically and carefully. This patience allowed him to develop a deep and comprehensive understanding of physics. His colleagues soon recognized his exceptional abilities. Although still relatively young, he earned a reputation as a thoughtful and rigorous thinker. He was respected not only for his technical knowledge, but also for his integrity and professionalism. These qualities helped establish the trust and credibility that would later prove essential when he introduced revolutionary ideas to the scientific world. The young Max Planck could not have known that he was preparing for one of the most significant scientific breakthroughs in history. Yet every stage of his early life contributed to that future achievement. His family's emphasis on education, his disciplined school years, his love of music, his fascination with thermodynamics, and his commitment to independent thinking all helped shape the scientist he would become. These experiences formed the foundation of a remarkable intellectual journey. They nurtured the curiosity, discipline, and determination that enabled Planck to confront some of the most difficult problems in physics. More importantly, they cultivated a mindset dedicated to seeking truth regardless of convention or expectation. As the 19th century drew to a close, physics stood on the threshold of transformation. The established theories of classical science appeared strong and complete, yet hidden challenges remained unresolved. Few scientists realized that a revolution was approaching. Among those preparing, perhaps unknowingly, to lead that revolution was Max Planck, a scholar whose early years had forged the qualities necessary to change humanity's understanding of the universe forever. As Max Planck advanced through the early stages of his academic career, he became increasingly committed to the pursuit of scientific truth. Unlike many researchers who focused on achieving fame or rapid success, Planck believed that science was a lifelong search for the fundamental principles governing the universe. This perspective distinguished him from many of his contemporaries and shaped the way he approached every scientific challenge he encountered. Following the completion of his doctoral studies, Planck continued his research while seeking opportunities within the academic world. During this period, he worked as a private docent, a position that allowed him to lecture at universities while conducting independent research. Although the role provided intellectual freedom, it offered limited financial security and required significant dedication. Many young scholars found this stage of their careers difficult, but Planck remained patient and focused on developing his expertise. His early investigations centered largely on thermodynamics, particularly the concept of entropy. At the time, thermodynamics represented one of the most advanced and intellectually demanding areas of physics. Scientists were attempting to understand the behavior of heat, energy transfer, and the laws governing physical systems. Planck became deeply fascinated by these questions because they addressed the fundamental structure of nature itself. The concept of entropy was especially intriguing to him. Entropy describes the tendency of systems to move towards states of greater disorder. For example, heat naturally flows from a hotter object to a colder one rather than the reverse. This tendency reflects a universal principle that appears throughout nature. Planck viewed the second law of thermodynamics as one of the most profound scientific discoveries ever made because it seemed to reveal a fundamental truth about how the universe operates. His dedication to understanding thermodynamics demonstrated a characteristic that would define his entire career. Rather than being satisfied with surface-level explanations, he sought the deepest possible understanding of physical laws. He wanted to know not only what happened in nature, but why it happened. This relentless search for underlying principles became a driving force behind his scientific achievements. During the 1880s, Planck gradually gained recognition within academic circles. His research papers attracted attention for their precision, clarity, and originality. Fellow scientists respected his ability to analyze complex problems and develop rigorous theoretical arguments. Although he had not yet made the discovery that would transform physics, he was steadily building a reputation as one of Germany's most promising theoretical physicists. In 1885, Planck received an appointment as an associate professor at the University of Kiel. Returning to the city of his birth marked an important milestone in his career. The position provided greater stability and allowed him to expand both his teaching and research activities. At Kiel, he continued investigating thermodynamic phenomena while refining his scientific methods and developing his own intellectual identity. Teaching played a significant role in Planck's professional life. He took his responsibilities as an educator very seriously and believed that scientific knowledge should be communicated with accuracy and clarity. His lectures were known for their careful organization and logical structure. Students appreciated his ability to explain difficult concepts while maintaining rigorous academic standards. Planck's approach to teaching reflected his broader philosophy regarding science. He believed that genuine understanding required discipline, patience, and careful reasoning. Scientific knowledge was not something to be accepted blindly. It had to be examined critically and supported by evidence. This commitment to intellectual honesty earned him widespread respect among colleagues and students alike. In 1889, another major opportunity emerged. Following the death of the prominent physicist Gustav Kirchhoff, Planck was invited to assume one of the most prestigious positions in German science at the University of Berlin. This appointment represented a turning point in his career. Berlin was not only Germany's leading scientific center, but also one of the most important research institutions in the world. Accepting the position placed Planck at the heart of the international scientific community. He now worked alongside some of the most respected scholars of his era and had access to the latest research developments. The environment challenged him intellectually and encouraged him to tackle increasingly complex scientific problems. At Berlin, Planck devoted himself to research while continuing his teaching responsibilities. He quickly established himself as a leading authority on thermodynamics and theoretical physics. His reputation for precision and integrity grew steadily, and he became known as a scientist whose conclusions were carefully reasoned and thoroughly supported by evidence. One of the most remarkable aspects of Planck's personality was his commitment to objectivity. He believed that scientific truth existed independently of personal opinions or preferences. The role of the scientist was to discover that truth through observation, experimentation, and logical analysis. This belief guided every aspect of his work and influenced his approach to scientific inquiry. At the same time, Planck maintained interests beyond science. Music continued to occupy an important place in his life. He frequently performed classical compositions and remained deeply connected to the cultural traditions of Germany. His appreciation for music provided balance and inspiration, allowing him to approach scientific challenges with creativity as well as discipline. Many historians have noted the similarities between Planck's musical and scientific sensibilities. Both fields involve patterns, structures, and underlying harmonies. Just as a composer organizes notes into meaningful arrangements, a scientist seeks to uncover the hidden order governing natural phenomena. For Planck, these pursuits were complementary expressions of humanity's desire to understand and appreciate the world. As the 19th century approached its final years, the scientific landscape appeared increasingly stable. Classical physics had achieved remarkable successes in explaining motion, electricity, magnetism, and thermodynamics. Many experts believed that only minor details remained to be resolved. The major laws of nature seemed firmly established. Yet beneath this appearance of certainty, significant problems remained unsolved. Experimental observations were beginning to reveal phenomena that classical theories could not adequately explain. Small inconsistencies emerged between theoretical predictions and actual measurements. Although these discrepancies appeared minor at first, they hinted at deeper issues within the foundations of physics. Planck was among the scientists who took these challenges seriously. Rather than dismissing unexplained results, he viewed them as opportunities for discovery. His willingness to confront difficult questions reflected his intellectual courage and dedication to truth. He understood that scientific progress often begins with anomalies that challenge accepted assumptions. This mindset distinguished him from those who believed existing theories were complete. Planck respected the achievements of classical physics, but he remained open to the possibility that new insights might be necessary. His commitment to evidence allowed him to follow scientific reasoning wherever it led, even when it contradicted long-established beliefs. Another important aspect of Planck's character was perseverance. Scientific research frequently involves setbacks, frustrations, and long periods without obvious progress. Many researchers become discouraged when confronted with persistent difficulties. Planck, however, possessed extraordinary patience. He approached problems methodically and remained focused even when solutions seemed distant. This perseverance would later prove essential when he confronted one of the most challenging puzzles in physics. The breakthrough that made him famous did not emerge suddenly or by accident. It resulted from years of preparation, study, and intellectual discipline. His early experiences had trained him to persist in the face of uncertainty and complexity. Planck also understood the importance of humility in scientific work. Despite his growing reputation, he never assumed that he possessed all the answers. He recognized that nature is often more complex and surprising than human expectations. This humility enabled him to reconsider assumptions and embrace new ideas when evidence demanded it. By the end of the 19th century, Max Planck had become one of Europe's most respected theoretical physicists. He was admired for his scholarship, teaching, integrity, and commitment to scientific excellence. Yet his most significant achievement still lay ahead. The qualities developed throughout his early life, curiosity, discipline, patience, independence, and courage, had prepared him for a challenge that would transform science forever. The young boy who had grown up in an academic family, studied diligently in Munich, pursued knowledge for its own sake, and dedicated himself to understanding thermodynamics, was now positioned at the center of the scientific world. Every stage of his journey had contributed to his development as a thinker and researcher. The lessons learned during his formative years would soon guide him toward a revolutionary discovery. Looking back, it becomes clear that the birth of a scientific visionary was not defined by a single moment, but by a continuous process of growth and preparation. Max Planck's early life demonstrates that greatness is often built upon years of dedication, learning, and perseverance. His story reminds us that extraordinary achievements are rarely the result of talent alone. They emerge from a combination of curiosity, hard work, integrity, and an unwavering commitment to understanding the truth. These qualities transformed Max Planck from a talented student into one of history's greatest scientists. More importantly, they prepared him to challenge conventional wisdom and open an entirely new chapter in humanity's understanding of the universe. The foundation had been laid, the vision had been formed, and the stage was set for a scientific revolution that would change the world forever. The crisis of classical physics to fully appreciate Max Planck's revolutionary contributions to science. It is essential to understand the scientific environment that existed before the birth of quantum theory. During the 19th century, physics was widely regarded as one of humanity's greatest intellectual achievements. Scientists had developed powerful theories that appeared capable of explaining nearly every observable phenomenon in nature. The laws established by generations of researchers provided a coherent picture of the universe and inspired enormous confidence in the future of scientific progress. For many physicists, it seemed that the fundamental mysteries of nature had already been solved. The remaining work appeared to involve refining measurements, improving calculations, and filling minor gaps in existing knowledge. Yet beneath this atmosphere of confidence, hidden problems were beginning to emerge. These problems challenged the foundations of classical physics and ultimately led to one of the most profound revolutions in scientific history. Classical physics refers to the collection of scientific theories developed before the 20th century. Its foundations were established by some of history's greatest thinkers. The work of Isaac Newton provided a mathematical framework for understanding motion and gravity. Newton's laws explained the movement of planets, falling objects, and countless mechanical systems with remarkable accuracy. Later, scientists expanded this framework through new discoveries in electricity, magnetism, heat, and energy. One of the most important achievements came from James Clerk Maxwell, whose equations unified electricity and magnetism into a single theory known as electromagnetism. Maxwell's work demonstrated that light itself was an electromagnetic wave, linking previously separate areas of science into a unified understanding of nature. Together, Newtonian mechanics, thermodynamics, and Maxwell's electromagnetic theory created a powerful scientific world view. These theories successfully explained an enormous range of phenomena. Engineers used them to design machines, construct bridges, develop communication systems, and drive industrial progress. Their success was so impressive that many scientists believed physics was approaching completion. A famous statement often attributed to physicists of that era suggested that there remained only a few small clouds on the horizon of scientific knowledge. Most experts assumed that these minor difficulties would soon be resolved within the existing framework. They did not realize that these clouds concealed a storm capable of transforming science forever. One reason for this confidence was the extraordinary predictive power of classical physics. Newton's equations could accurately forecast planetary motions years in advance. Maxwell's electromagnetic theory successfully explained the behavior of light and electrical phenomena. Thermodynamics provided universal principles governing heat and energy transfer. Everywhere scientists looked, classical theories seemed to work remarkably well. However, science advances not only through success, but also through failure. Occasionally, experiments reveal results that established theories cannot explain. When such discrepancies arise, scientists must either modify existing theories or develop entirely new ones. By the late 19th century, several important discrepancies had begun to attract attention. One of the most troubling challenges involved the study of thermal radiation. Scientists were investigating how heated objects emit energy in the form of electromagnetic radiation. Everyday examples include glowing metal, burning coal, and the light produced by stars. Researchers sought to understand the precise relationship between temperature and the radiation emitted by an object. To simplify the problem, physicists developed the concept of a blackbody. A blackbody is an idealized object that absorbs all incoming radiation and emits energy according to its temperature. Although no perfect blackbody exists in nature, the concept provided a useful theoretical model for scientific investigation. Experimental measurements of blackbody radiation produced highly accurate data. Scientists carefully recorded the intensity of radiation emitted at different wavelengths and temperatures. The challenge was to develop a theoretical explanation that matched these observations. Initially, physicists expected classical theories to solve the problem without difficulty. After all, classical physics had successfully explained countless other phenomena. Yet, as researchers attempted to apply existing principles to blackbody radiation, serious problems emerged. Several theoretical models were proposed, but none successfully reproduced the experimental results across all wavelengths. Some equations worked well at certain frequencies, but failed dramatically at others. The discrepancy became increasingly difficult to ignore as experimental measurements improved. One particularly troubling prediction arose from classical electromagnetic theory. According to the calculations of physicists Lord Rayleigh and James Jeans, a blackbody should emit increasingly large amounts of energy at shorter wavelengths. In fact, the theory predicted that the emitted energy would become infinitely large as wavelength approached zero. This prediction was clearly impossible. Real objects do not emit infinite amounts of energy. Experimental observations showed that radiation intensity rises to a peak and then decreases at shorter wavelengths. The classical prediction was completely inconsistent with reality. The contradiction became known as the ultraviolet catastrophe. The term reflects the fact that classical theory predicted absurd amounts of energy in the ultraviolet region of the electromagnetic spectrum. This failure represented far more than a minor technical problem. It revealed a fundamental weakness in the theoretical foundations of physics. The ultraviolet catastrophe was alarming because it emerged from principles that scientists had trusted for decades. The equations involved were not obscure or experimental. They were based on the core assumptions of classical physics itself. If these assumptions produced impossible results, then something essential was missing from the scientific understanding of nature. At the same time, other unexplained phenomena were creating additional challenges. One important example involved the photoelectric effect. Experiments showed that light striking certain metals could eject electrons from their surfaces. However, the behavior observed in these experiments could not be fully explained using classical wave theory. According to classical expectations, increasing the intensity of light should increase the energy transferred to electrons. Yet experiments revealed that the frequency of light was more important than its intensity. Low frequency light failed to eject electrons regardless of brightness, while high frequency light could produce immediate electron emission even at low intensities. These observations contradicted classical predictions and suggested that light might possess properties not described by existing theories. Scientists recognized the significance of the problem but lacked a satisfactory explanation. Another challenge emerged from studies of atomic structure. Classical electromagnetic theory predicted that electrons orbiting atomic nuclei should continuously radiate energy. As they lost energy, they would spiral inward and collapse into the nucleus. If this prediction were correct, atoms should be unstable. Yet atoms are obviously stable. Matter exists because atoms maintain their structure over long periods. The inability of classical physics to explain atomic stability represented another serious deficiency. Once again, experimental reality conflicted with theoretical expectations. These problems shared an important characteristic. They all involved phenomena occurring at extremely small scales or under unusual conditions. Classical physics continued to perform remarkably well when applied to everyday objects and large-scale systems. Its predictions remained accurate for planets, machines, projectiles, and most ordinary experiences. The crisis emerged when scientists examined the microscopic world. At these scales, nature behaved in unexpected ways that classical theories could not adequately describe. The closer researchers looked, the more apparent these inconsistencies became. For many scientists, these difficulties were deeply unsettling. Classical physics had been regarded as a nearly complete description of reality. Discovering fundamental flaws within such a successful framework forced researchers to reconsider assumptions that had long been taken for granted. Yet, scientific crises often create opportunities for progress. When existing theories fail, new ideas become possible. Problems that appear threatening can stimulate creativity and innovation. The unresolved mysteries confronting physicists at the end of the 19th century created precisely such an environment. Max Planck entered this scientific landscape at a crucial moment. As a leading expert in thermodynamics and theoretical physics, he was uniquely positioned to address some of the most difficult questions facing the scientific community. His rigorous training, analytical abilities, and dedication to fundamental principles prepared him for the challenge. Importantly, Planck did not begin his work with the intention of overthrowing classical physics. Like most scientists of his era, he respected its achievements and assumed that its foundations were fundamentally sound. His goal was simply to solve specific problems related to thermal radiation and energy distribution. However, the deeper he investigated these issues, the clearer it became that traditional approaches were inadequate. Existing theories could not explain the experimental evidence. New ideas would be required, even if they challenged long-established assumptions. The growing crisis within classical physics set the stage for one of the greatest breakthroughs in scientific history. The unresolved mysteries surrounding blackbody radiation, atomic behavior, and electromagnetic phenomena created a need for fresh thinking. Scientists stood at the threshold of a new era, though few realized it at the time. As the 19th century came to an end, confidence in classical physics remained strong, but cracks had begun to appear in its foundation. The apparent completeness of scientific knowledge was revealed to be an illusion. Beneath the surface, nature was hiding secrets that would soon transform humanity's understanding of reality itself. In this atmosphere of uncertainty, challenge, and intellectual tension, Max Planck began the work that would ultimately lead to the birth of quantum theory. The crisis confronting classical physics was not merely a problem to be solved. It was the doorway to an entirely new vision of the universe. As the 19th century moved toward its conclusion, the scientific community found itself in a situation unlike any it had experienced before. For generations, classical physics had provided a reliable framework for understanding nature. Its equations described motion, energy, electricity, magnetism, and countless other phenomena with remarkable accuracy. Scientists trusted these theories because they consistently matched experimental observations in the world around them. Yet a growing collection of unexplained results suggested that this confidence might have been misplaced. The difficulty was not that classical physics had suddenly stopped working. In fact, it continued to perform exceptionally well in many areas. Engineers could still design machines using Newtonian mechanics. Astronomers could still calculate planetary orbits. Electrical systems could still be understood through Maxwell's equations. The problem was that certain experiments revealed behaviors that simply did not fit within the established framework. This created a profound intellectual dilemma. If classical theories worked so well in most situations, how could they fail so dramatically in others? Scientists were forced to confront the possibility that the laws they believed were universal might actually have limits. Such a realization challenged deeply held assumptions about the nature of scientific knowledge. One of the reasons the crisis became so significant was the increasing precision of experimental techniques. During the 19th century, technological advances allowed researchers to perform measurements with unprecedented accuracy. Instruments became more sensitive, data became more reliable, and experimental results could be verified repeatedly. As a consequence, discrepancies that might once have been dismissed as measurement errors could no longer be ignored. Experimental evidence consistently demonstrated that certain phenomena behaved differently from what classical physics predicted. The conflict between theory and observation became impossible to overlook. The study of blackbody radiation remained one of the most serious examples. Physicists devoted considerable effort to understanding how energy was distributed across different wavelengths of light emitted by heated objects. Laboratories throughout Europe conducted experiments to collect increasingly precise measurements. The data revealed a clear pattern. As temperature increased, the distribution of emitted radiation changed in predictable ways. However, none of the available classical theories could accurately describe the entire spectrum. Equations that worked at longer wavelengths failed at shorter wavelengths, while those designed for short wavelengths performed poorly elsewhere. Scientists recognized that this was not merely a mathematical inconvenience. The inability to explain blackbody radiation suggested that something fundamental was missing from their understanding of energy itself. Since energy played a central role in virtually every branch of physics, the implications were enormous. The ultraviolet catastrophe highlighted this problem in dramatic fashion. According to classical assumptions, energy could vary continuously and could be distributed among electromagnetic waves without restriction. When these assumptions were applied mathematically, they produced impossible predictions involving infinite amounts of energy. Infinity in physics is often a warning sign that a theory has broken down. Nature does not appear to contain infinite quantities of energy within ordinary physical systems. Therefore, when calculations produce such results, scientists must examine the assumptions underlying the theory. The ultraviolet catastrophe forced physicists to question one of their most basic beliefs, the idea that energy changes continuously. For centuries, continuity had been regarded as a natural feature of physical reality. Objects could move through space continuously, waves could vary smoothly, and energy could increase or decrease by arbitrarily small amounts. This assumption seemed so obvious that few scientists had ever considered alternatives, yet the failure of classical theory suggested that continuity might not be universally valid. Although the implications were not yet fully understood, the possibility of a fundamentally different picture of nature began to emerge. At the same time, investigations into atomic phenomena created additional difficulties. Scientists increasingly viewed atoms as the building blocks of matter. Understanding their structure and behavior became one of the central goals of physics. However, classical theories struggled to explain atomic stability. According to electromagnetic principles, accelerating electric charges should emit radiation and lose energy. Electrons moving around atomic nuclei were accelerating charges. Therefore, they should continuously radiate energy and spiral inward toward the nucleus. If this prediction were correct, atoms would collapse almost instantly. Matter as we know it could not exist. Yet atoms clearly remained stable over long periods. The contradiction revealed another fundamental limitation within classical physics. Researchers also encountered puzzles involving the behavior of gases and the statistical properties of large collections of particles. Classical theories often assumed that energy could be shared continuously among particles. In some cases, these assumptions produced results that disagreed with observations. Such discrepancies suggested that the crisis extended beyond a single phenomenon. The problems were interconnected and pointed toward deeper issues within the foundations of physics. Scientists could no longer assume that isolated adjustments would solve the difficulties. A more comprehensive solution seemed necessary. The scientific atmosphere during this period was both exciting and unsettling. On one hand, researchers recognized that they were confronting profound mysteries. On the other hand, they lacked a clear path forward. Existing theories appeared incomplete, but no satisfactory replacement had yet emerged. Different scientists proposed various solutions. Some attempted to modify classical equations while preserving their underlying assumptions. Others suggested entirely new approaches. Debates intensified as physicists searched for explanations that could reconcile theory with experiment. Max Planck found himself at the center of this intellectual struggle. As a respected theoretical physicist specializing in thermodynamics, he was deeply interested in the problems associated with radiation and energy distribution. His expertise made him uniquely qualified to investigate the questions troubling the scientific community. Planck approached these challenges with characteristic rigor and determination. He believed that nature followed objective laws and that careful analysis would eventually reveal them. Rather than becoming discouraged by contradictions, he viewed them as opportunities to deepen scientific understanding. One of his strengths was his willingness to focus on specific problems while maintaining awareness of broader principles. Instead of attempting to revolutionize physics directly, he concentrated on developing an accurate theoretical description of blackbody radiation. His immediate goal was practical: find an equation that matched experimental data. Yet achieving this goal proved extraordinarily difficult. Existing models repeatedly failed to reproduce observations across the full range of wavelengths. Planck experimented with different mathematical approaches, searching for a solution that would satisfy both theory and experiment. The challenge forced him to examine assumptions that many scientists accepted without question. In doing so, he gradually moved closer to ideas that would transform physics forever. Although he did not initially realize it, his efforts were leading him toward a completely new conception of energy. The crisis of classical physics also had important philosophical implications. For centuries, many scientists had believed that nature could be understood through deterministic laws. Given sufficient information about a system, one could predict its future behavior with certainty. This world-view had been reinforced by the success of Newtonian mechanics and other classical theories. However, the growing collection of anomalies suggested that reality might be more complex than previously imagined. The microscopic world appeared to operate according to principles that differed from those governing everyday experience. Concepts that seemed self-evident at large scales became questionable when applied to atoms and radiation. This realization required scientists to adopt a new level of intellectual flexibility. They could no longer assume that familiar ideas would remain valid under all circumstances. Instead, they had to remain open to the possibility that nature possessed unexpected properties waiting to be discovered. The difficulties confronting classical physics also demonstrated an important feature of scientific progress. Science does not advance through certainty alone. Often, major breakthroughs emerge when existing theories encounter problems they cannot solve. Anomalies and contradictions serve as catalysts for innovation because they force researchers to reconsider established beliefs. The history of physics provides many examples of this process. Newtonian mechanics replaced earlier explanations of motion because it accounted for observations more successfully. Maxwell's theory unified electricity and magnetism by resolving inconsistencies between previous models. Similarly, the crisis at the end of the 19th century created conditions that would eventually give rise to quantum theory. By the time the century ended, it had become increasingly clear that classical physics could not provide a complete description of nature. Its achievements remained impressive, but its limitations were undeniable. The unresolved problems involving blackbody radiation, atomic stability, and electromagnetic phenomena demanded new ideas. Scientists stood at a crossroads. One path involved continuing to modify existing theories in hopes of preserving traditional assumptions. The other required embracing fundamentally new concepts that might challenge centuries of scientific thinking. The choice was not easy, and many researchers resisted radical changes. Yet the evidence continued to accumulate. Experiments repeatedly demonstrated that nature behaved in ways classical physics could not explain. The pressure for a new framework grew stronger with each passing year. In retrospect, the crisis of classical physics was not a sign of failure, but a necessary stage in the evolution of scientific knowledge. It revealed the limits of existing theories and highlighted questions that demanded deeper investigation. Without these challenges, the development of quantum theory might never have occurred. The scientific world was approaching a turning point. The old framework, despite its many successes, could no longer account for all observed phenomena. New principles were needed to bridge the gap between theory and reality. At the center of this search stood Max Planck, whose determination to solve the puzzle of blackbody radiation would soon lead to one of the most revolutionary discoveries in human history. The stage was now set for a transformation that would alter our understanding of energy, matter, light, and the very nature of the universe. The crisis had exposed the weaknesses of classical physics, but it had also opened the door to an entirely new era of scientific exploration. The revolutionary quantum hypothesis at the dawn of the 20th century, physics faced a serious challenge. Classical theories that had successfully explained many natural phenomena were unable to account for the behavior of blackbody radiation. Scientists struggled to understand how heated objects emitted energy, and existing equations produced results that conflicted with experimental observations. It was within this scientific crisis that Max Planck introduced an idea that would forever change humanity's understanding of the universe. In 1900, while studying blackbody radiation, Planck sought a mathematical solution that would accurately match experimental data. After extensive analysis, he proposed a bold and unexpected hypothesis. He suggested that energy is not emitted or absorbed continuously, as classical physics assumed. Instead, energy is exchanged in tiny, discrete packets, which he called quanta. This idea represented a radical departure from traditional scientific thinking. According to classical physics, energy could vary smoothly and continuously, much like water flowing through a river. Planck's proposal challenged this assumption by suggesting that energy behaves more like individual units or particles. Just as a staircase consists of separate steps rather than a smooth slope, energy could only exist in specific amounts rather than any possible value. Planck further proposed that the energy of each quantum was proportional to the frequency of radiation. This relationship became one of the most important equations in physics and introduced a new fundamental constant, now known as Planck's constant. This constant plays a central role in quantum mechanics and remains one of the basic constants of nature. Initially, Planck viewed his hypothesis as a mathematical technique rather than a description of physical reality. He introduced the concept primarily to solve the blackbody radiation problem and obtain results that matched experiments. To his surprise, the hypothesis worked perfectly. It explained observations that classical theories could not, providing a solution to one of the most difficult problems in physics. The significance of Planck's idea became increasingly clear in the years that followed. Scientists realized that quantization was not merely a mathematical convenience, but a fundamental property of nature. The concept inspired further research and led to groundbreaking discoveries. Albert Einstein used quantum ideas to explain the photoelectric effect, while later physicists expanded the theory into a comprehensive framework known as quantum mechanics. The quantum hypothesis transformed science by revealing that the microscopic world operates according to principles very different from those observed in everyday life. It challenged long-standing assumptions about energy, matter, and light, opening entirely new avenues of research. Modern technologies such as semiconductors, lasers, medical imaging devices, and quantum computers all trace their origins to this revolutionary insight. Max Planck's quantum hypothesis marked the beginning of a new era in physics. What started as an attempt to solve a specific scientific problem became one of the most important breakthroughs in human history. By introducing the concept of energy quanta, Planck laid the foundation for quantum theory and forever changed our understanding of the natural world. The father of quantum theory, Max Planck, is widely recognized as the father of quantum theory, a title earned through his groundbreaking contribution to modern physics at the beginning of the 20th century. His revolutionary ideas transformed scientific understanding and laid the foundation for one of the most important fields of study in human history. Although many scientists later expanded and developed quantum mechanics, it was Planck who took the first decisive step that opened the door to an entirely new understanding of nature. Before Planck's work, Physicists relied on classical theories developed by scientists such as Isaac Newton and James Clerk Maxwell. These theories had successfully explained many natural phenomena, from planetary motion to electricity and magnetism. However, by the late 19th century, certain experimental results could not be explained using existing scientific principles. One of the most significant problems involved blackbody radiation, the energy emitted by heated objects. Scientists attempted to describe this radiation using classical physics, but their calculations failed to match experimental observations. Theoretical predictions suggested impossible results, including the emission of infinite energy at very short wavelengths. This contradiction became known as the ultraviolet catastrophe and revealed a serious flaw in classical physics. While investigating this problem, Planck introduced a bold new idea in 1900. He proposed that energy is not emitted or absorbed continuously, but in small, discrete packets called quanta. This hypothesis allowed him to develop a mathematical formula that accurately described blackbody radiation and matched experimental data. Although Planck initially viewed the idea as a useful mathematical assumption, it soon became clear that it represented something much more profound. Planck's discovery challenged one of the most fundamental beliefs of classical science. For centuries, energy had been considered continuous, capable of changing by any amount. By suggesting that energy existed in specific units, Planck introduced a completely new way of thinking about the physical world. This concept became the foundation of quantum theory. The importance of Planck's work grew rapidly as other scientists explored its implications. Albert Einstein applied quantum ideas to explain the photoelectric effect, demonstrating that light itself could behave as discrete packets of energy. Niels Bohr used quantum principles to develop a new model of the atom. Later, Werner Heisenberg, Erwin Schrödinger, and many others expanded these ideas into the full framework of quantum mechanics. Although these scientists made significant contributions, they all built upon the foundation established by Planck. Without his original insight, the development of quantum physics would not have been possible. His work initiated a scientific revolution that fundamentally altered humanity's understanding of matter, energy, and the structure of the universe. Planck's influence extends far beyond theoretical science. Quantum theory has enabled countless technological advances, including transistors, semiconductors, lasers, medical imaging systems, and modern computers. Many of the technologies that define contemporary life exist because of the scientific framework that originated with Planck's discovery. For his extraordinary achievements, Planck received the Nobel Prize in Physics in 1918. More importantly, he earned a permanent place in scientific history as the pioneer who introduced the concept of quantized energy. His courage to challenge established assumptions and follow evidence wherever it led transformed physics forever. That is why Max Planck is remembered around the world as the father of quantum theory, a visionary whose ideas opened a new chapter in humanity's quest to understand the universe. Inspiring a new generation of scientists, one of Max Planck's greatest contributions to science was not only his revolutionary discoveries, but also the inspiration he provided to future generations of scientists. His groundbreaking work on quantum theory opened entirely new fields of research and encouraged some of the most brilliant minds of the 20th century to explore questions that had previously seemed impossible to answer. Through his ideas, leadership, and dedication to scientific truth, Planck became a guiding influence for researchers around the world. When Planck introduced the quantum hypothesis in 1900, Many scientists were surprised by the radical nature of his proposal. The idea that energy could exist in discrete packets challenged long-established beliefs about the physical world. Although some researchers were initially skeptical, younger scientists recognized the enormous potential of this new way of thinking. Planck's work demonstrated that even the most accepted scientific theories could be questioned when experimental evidence demanded it. Among the scientists inspired by Planck was Albert Einstein. In 1905, Einstein extended Planck's quantum concept to explain the photoelectric effect, showing that light itself could behave as individual packets of energy. This discovery became one of the key foundations of modern quantum physics. Einstein often acknowledged the importance of Planck's original work and recognized that it had opened a completely new direction for scientific research. Another scientist greatly influenced by Planck was Niels Bohr. Building on quantum ideas, Bohr developed a revolutionary model of the atom that explained how electrons occupy specific energy levels. His work helped scientists understand atomic structure and provided further evidence that quantum principles governed the microscopic world. Bohr's achievements would not have been possible without the foundation created by Planck. The influence of Planck extended even further through scientists such as Werner Heisenberg, Erwin Schrödinger, Wolfgang Pauli, and Max Born. These researchers expanded quantum theory into a complete scientific framework known as quantum mechanics. Their discoveries transformed physics and reshaped humanity's understanding of matter, energy, and reality itself. In many ways, they were continuing a journey that Planck had begun. Beyond his scientific contributions, Planck served as a mentor and role model. He encouraged intellectual curiosity, rigorous thinking, and a commitment to truth. Young scientists admired his integrity and dedication to research. He demonstrated that scientific progress requires patience, discipline, and the courage to challenge established ideas when evidence points in a new direction. Planck also played an important role in academic institutions and scientific organizations. Through his leadership, he helped create environments where innovative ideas could flourish. He supported talented researchers and contributed to the growth of scientific communities that fostered collaboration and discovery. His influence was felt not only through his own work, but also through the opportunities he helped create for others. The impact of Planck's inspiration continues today. Modern fields such as quantum computing, quantum cryptography, nanotechnology, and advanced materials science all trace their origins to the scientific revolution he initiated. Researchers around the world continue to build upon the foundations of quantum theory, exploring questions that Planck could scarcely have imagined. Max Planck's legacy is therefore not limited to a single discovery. He inspired generations of scientists to think differently, question assumptions, and pursue knowledge with determination and honesty. His example demonstrates how one individual's commitment to understanding nature can influence countless others and shape the future of science for generations to come. Recognition, challenges, and leadership. Max Planck's journey as a scientist was marked not only by groundbreaking discoveries, but also by significant recognition, personal challenges, and exceptional leadership. While he is best known as the founder of quantum theory, his influence extended far beyond his scientific achievements. Throughout his life, Planck earned the respect of the international scientific community, overcame numerous hardships, and provided guidance during some of the most difficult periods in modern history. As Planck's revolutionary work on quantum theory gained acceptance, his reputation as one of the world's leading physicists grew steadily. Scientists increasingly recognized the importance of his discovery that energy is emitted and absorbed in discrete units known as quanta. What began as an attempt to solve the problem of blackbody radiation eventually became the foundation of modern quantum physics. As the significance of his contribution became clear, Planck received widespread admiration from fellow researchers and academic institutions across Europe and beyond. One of the greatest honors of his career came in 1918 when he was awarded the Nobel Prize in Physics. The Nobel Committee recognized his groundbreaking work in developing quantum theory and acknowledged its profound impact on scientific understanding. This award confirmed Planck's place among the most influential scientists in history and highlighted the importance of his contributions to modern physics. In addition to receiving prestigious awards, Planck held several important academic positions. He served as a professor at the University of Berlin, one of Europe's most respected centers of scientific research. Through his teaching and mentorship, he influenced countless students and young scientists. His lectures were known for their clarity, precision, and intellectual depth, helping to shape the next generation of physicists. Despite his professional success, Planck's life was filled with personal difficulties and tragedies. He lived through a period of immense political and social upheaval, including both World War I and World War II. These conflicts brought enormous suffering to Europe and affected nearly every aspect of daily life. Like many individuals of his generation, Planck witnessed the destruction caused by war and experienced the uncertainty that accompanied these turbulent times. His personal losses were particularly heartbreaking. Several members of his family died during his lifetime, including children whom he loved deeply. These tragedies would have overwhelmed many people, yet Planck continued his scientific work and maintained his commitment to education and research. His ability to persevere through grief demonstrated remarkable strength of character and resilience. Planck also faced difficult ethical and professional challenges during the rise of political extremism in Germany. As a respected scientific leader, he sought to protect academic institutions and support fellow scholars during a period of increasing political pressure. Although the circumstances were extraordinarily complex, he remained committed to the values of knowledge, reason, and intellectual freedom. His leadership extended beyond the classroom and laboratory. Planck served in important scientific organizations and helped guide research communities during times of uncertainty. Colleagues admired his integrity, fairness, and dedication to scientific excellence. He understood that science thrives when researchers can pursue truth openly and collaborate freely, regardless of political or social circumstances. The respect he earned from fellow scientists was based not only on his discoveries, but also on his character. Planck was known for his humility, honesty, and professionalism. Even after achieving international fame, he remained devoted to learning and continued supporting younger researchers. His example demonstrated that true leadership involves service, responsibility, and a commitment to helping others succeed. Max Planck's life illustrates that great scientific achievement often requires perseverance in the face of adversity. His recognition reflected the importance of his discoveries, while his challenges revealed his courage and determination. Through his leadership, he strengthened scientific institutions and inspired generations of researchers. His legacy is therefore not only one of intellectual brilliance, but also of resilience, integrity, and dedication to the advancement of human knowledge. Max Planck's extraordinary legacy extends far beyond the discovery that made him famous. While he is widely recognized as the founder of quantum theory, His true impact lies in how his ideas transformed science, technology, and humanity's understanding of the universe. More than a century after his groundbreaking work, Planck's influence continues to shape modern research and everyday life, making him one of the most important figures in the history of science. The foundation of Planck's legacy was established in 1900 when he introduced the revolutionary concept that energy is emitted and absorbed in discrete units called quanta. At the time, this idea was proposed as a solution to the problem of blackbody radiation. However, scientists soon realized that it represented something much deeper. Planck had uncovered a fundamental property of nature that challenged centuries of scientific assumptions and opened the door to an entirely new field of physics. His quantum hypothesis became the starting point for quantum theory, one of the most successful scientific frameworks ever developed. Building upon Planck's work, scientists such as Albert Einstein, Niels Bohr, Werner Heisenberg, Erwin, and many others expanded quantum ideas into a complete understanding of the microscopic world. Their discoveries transformed physics and revealed that atoms, electrons, and light behave according to principles very different from those observed in everyday life. One of the most remarkable aspects of Planck's legacy is its influence on modern technology. Quantum theory forms the foundation of countless innovations that have transformed society. Technologies such as transistors, semiconductors, lasers, solar cells, and computer chips all depend on principles derived from quantum physics. Without Planck's original insight, many of the devices that power modern civilization would not exist. Computers, smartphones, internet communications, medical imaging systems, and advanced scientific instruments all rely on technologies rooted in quantum mechanics. Every time people use digital devices, communicate electronically, or benefit from modern medical equipment, they are indirectly experiencing the impact of Planck's discoveries. His work demonstrates how a theoretical scientific breakthrough can eventually transform everyday life for billions of people. Planck's influence also extends into contemporary scientific research. Today, scientists continue exploring fields that emerged from the quantum revolution he initiated. Quantum computing promises to solve complex problems beyond the capabilities of traditional computers. Quantum cryptography offers new methods of secure communication. Researchers are developing advanced materials and investigating the deepest mysteries of matter, energy, and the universe using concepts that trace their origins to Planck's work. Beyond his scientific contributions, Planck left a lasting example of intellectual integrity and dedication to truth. He believed that science should be guided by evidence rather than personal beliefs or popular opinion. His willingness to follow experimental results, even when they challenged established theories, demonstrated extraordinary courage and honesty. These qualities continue to inspire scientists around the world. Planck's life also illustrates the importance of perseverance. He spent years studying difficult problems and remained committed to understanding nature despite professional challenges and personal tragedies. His determination reminds us that great discoveries often require patience, discipline, and unwavering dedication. Today, Max Planck is remembered not only as a brilliant physicist, but also as a visionary who changed humanity's view of reality. His discoveries reshaped science, inspired generations of researchers, and led to technologies that continue to improve lives across the globe. More than a century after introducing the quantum hypothesis, his influence remains as powerful as ever. Max Planck's extraordinary legacy is a testament to the enduring power of human curiosity and scientific inquiry. Through his groundbreaking ideas, he opened a new chapter in our understanding of the universe and left a legacy that will continue to inspire future generations for centuries to come.